right, everyone, in this video we are going to compare carbonyl reactivity, and our focus point is going to be on reactivity of aldehydes and ketones, but keep in mind that on your second exam you'll also have your carboxylic acid derivatives, and your carboxylic acid derivatives will be these carbonyl species to the left of aldehydes and ketones, and also to the right of aldehydes and ketones. Okay? Now, aldehydes and ketones are kind of mid-tier reactivity. There are two functional groups like the acid chloride and acid anhydride that would be more reactive than your aldehyde and ketone, and then you have your less reactive derivative species. Now, when we're comparing reactivity, we want to think about reactivity as being first and foremost a function of how partial positive the carbonyl carbon is. That relates directly to its electrophilicity. So as we're comparing reactivity, I want us first to make an analysis of the electronics, how positive the carbonyl carbon is, and then if need be, we can default to sterics as well to analyze reactivity. Now, let's say that you're looking at this comparison here between acetaldehyde and acetone. When you have a methyl group bonded to the carbonyl carbon, just a simple carbon-hydrogen chain, there will be a sigma donation. There's an inductive donation, and that would actually decrease reactivity. Anytime there's a donation towards the carbonyl carbon of electron density, that decreases reactivity. And because in acetone, which is a ketone, there are two inductively donating alkyl groups, that would make that less reactive than acetaldehyde. And if I were to compare formaldehyde to acetaldehyde, formaldehyde is more reactive because it does not have that donation event that acetaldehyde has. And if you were then to look at, say, your less reactive derivatives, like your carboxylic acid, your ester, your amide, what's happening there is there's a donating group. You have your OH or your OR, or the NH2 group, or the O- of a carboxylate resonance donating over the carbonyl. And when we have resonance donation over the carbonyl, that would decrease the electrophilicity of the carbonyl carbon. It's for that reason that those derivatives are less reactive. As you resonance donate over the carbonyl, you make that carbonyl less reactive, or making the carbon effectively less positive as we donate over. So we always want to think about electronics first and foremost, and then if you're comparing two functional groups that are the same, for example, here I have two aldehydes, or here I have two ketones, then maybe the analysis can come down to sterics, because if we're looking at these left two aldehydes, they both have an inductively donating group, yes. So their electronics are similar, but there's a difference in sterics. When you have a more bulky alkyl group, that larger alkyl group is going to net result lead to a decrease in the reactivity of the carbonyl carbon. Now, there's two reasons for that. Specifically, large alkyl groups can cause a destabilization of the transition state. In other words, we begin at the carbonyl carbon having 120-degree bond angles, and as we react generating the tetrahedral structure, the bond angle becomes 109.5. So because of that decrease in the bond angle, if you have a larger set of alkyl groups, those alkyl groups actually then start to run into other groups electronically speaking and cause sterics in the transition state as we rehybridize the carbonyl carbon from sp2 to sp3. So we can destabilize the transition state due to those alkyl groups having more sterics. And then you can imagine that with a larger alkyl group, inherently the nucleophile is going to have a harder time spatially accessing the carbonyl carbon. So there is both that spatial accessibility factor and the destabilization of the transition state factor as we have larger alkyl groups. And if I were to look at these two ketones, they're both ketones, each possessing two inductive donation events. So electronics is similar, but sterics is definitely different. What I see is here I've got a terbutyl group and an isopropyl group, whereas here I've got an isopropyl group and an ethyl group. And I would definitely say having a combination of isopropyl and terbutyl groups is going to cause more sterics, and therefore this would be less reactive than this ketone. So I would have you apply sterics when the functional group is the same. In other words, the electronics is the same. That's when we think about sterics. The other thing to keep in mind is that you could have groups that would inductively withdraw. So for example, you could have electron withdrawing groups like halogens, fluorines, chlorines, bromines, and iodines. And those groups would have an inductive withdrawal, pulling electron density away from the carbonyl carbon, and that would magnify the extent of deficiency at the carbonyl carbon. 3 fluorines would cause a larger withdrawal than just 1 fluorine, right? So maybe the partial positive is that big. And we know that with our halogens, strength is a factor. Remember, from an electronegativity standpoint, fluorine is the most electronegative, so fluorine would pull more than chlorine would. and chlorine would pull more inductively than bromine would, and iodine would pull the least. So the difference in reactivity of these species here is a function of the power and the strength of that withdrawal. Fluorine pulls more than chlorine, and chlorine withdraws more than bromine. Now, we can make the statement that in general, aldehydes are more reactive than ketones. But if I were to draw in this ketone for you here, this ketone with two CF3 groups, that's going to be way more reactive than even, say, formaldehyde, right? Formaldehyde, there's no withdrawal from the carbonyl carbon. Those hydrogens have no net effect. But with two CF3 groups, there is going to be a massive amount of electron withdrawal. So while that is a ketone, that would be more reactive than this aldehyde. And so the withdrawal aspect that we're looking at factors directly into the electronics, right? If there's withdrawal, we want to keep that in mind. And certain ketones, especially if there's withdrawal on both sides, can be more reactive than an aldehyde. Now, for the record, you could also see an inductively withdrawing group like this. You could possibly have CN attachments. On a former exam, professors gave a structure with multiple CN groups. Now, keep in mind that those CN groups are really C triple bond N functional groups. And here, those are not going to have a resonance effect on reactivity, but rather, because of that polarization of the carbon-nitrogen triple bond, the CN group can have a sigma electron withdrawal effect. And so this would be, say, more reactive than this aldehyde that is lacking those CN groups. And you could even modulate reactivity thinking about, well, if there were two CN groups, that would be less reactive than just having one. And if there were one CN group, well, that would be, sorry about that, that would be more reactive than if there were no CN groups attached there. Okay, this was a reactivity question essentially on a former exam comparing these four structures. I know that's a little bit messy to track, but here with the three CNs, there's more withdrawal and more reactivity. With two CNs, there's more withdrawal and more reactivity than having one CN. And that CN group being present makes that more reactive than that aldehyde that is not having any CN groups directly. So we always first consider electronics and then sterics. And on your exam, you want to be prepared to have a ranking question or reactivity comparison with all the carbonyls mixed in. We'll go through more questions like that later once we get to the derivative chapters. For now, we're kind of focusing on aldehydes and ketones, but the factors that affect reactivity of aldehydes and ketones also translate more to the derivatives, but there's a further discussion to be had with derivative reactivity a little later.